In discussing Newton's universal gravitation, we need to understand what the hell that actually is, which is that Newton theorized that not planets have gravity, but that every mass has gravity. Every mass is attracted to every other mass in the universe, proportional to their masses, and inversely proportional to the square of the distances between them. Mathematically stated, we would have a proportional statement of proportionality like this. Mathematically, this means that if we take force times displacement, distance between the masses squared divided by the product of the masses, whatever two masses we're talking about, we will get the same value every time, capital G, which has become known as Newton's universal gravitational constant. Cavendish actually established this number as 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared, and that is a value that would be given to you on tests and quizzes. Turning that equation back together, then we get an equation for Newton's universal gravitational force of attraction between any two masses as, of course, the proportionality constant times the product of the masses divided by the distance between the centers squared. So for an object and Earth, that would be what we would call weight force. And weight force would be capital G times the mass of the object times the mass of the Earth divided by the radius of the Earth squared, the distance from the center of the Earth. Since weight force is mass times gravity, that gives us an equation for gravity, and we understand that gravity is inversely proportional to the distance we are away from the center of the Earth. So, what would be the weight of a 12 Newton object that is raised to a height of radius of the Earth above the surface of the Earth? So, in other words, we have double the distance the object is from the center of the Earth. We understand, of course, that if we go farther away from the center of the Earth, the force of attraction to the center of Earth, becomes less. And since it's an inverse square relationship, doubling the distance would mean we would have 1/4 the force of attraction. So again, well, obviously the mass of the object would not change. Its weight would, its force of attraction to the Earth, and that would be 3 newtons. Again, weight is really simply a shortcut of saying gravitational force of attraction between an object and a planet. Now, what would be the weight, going the other way around, of a 5-kilogram groundhog that burrows down a distance of half the radius towards the center of the Earth? This is a savage groundhog, obviously, being able to burrow this about 1,800 miles towards the center of the Earth. Our instinct is to say, well, if we cut the distance in half, the weight will go up 4 times. So this 50 Newton groundhog would have a weight of 500 newtons. Now that's not true. And why isn't it? Well, Newton theorized that when an object travels closer to the center of a planet, for example, the mass that the person is using is the mass that is quote-unquote inside the shell. So the mass above, so to speak, the groundhog isn't factored into this calculation. With this idea in mind, this is known as Newton's shell theorem, then we can calculate what the groundhog would weigh by understanding how much mass the groundhog would be attracted to. The radius of the shell is half the radius of the Earth. So the volume of the Earth, if we think about it as a sphere, would be 4/3 pi r squared. So the volume of the Earth is 4/3 pi radius of the Earth cubed, not squared, I'm sorry. And the volume of the shell would be 4/3 pi radius of the shell cubed. The 4/3 pi cancels out of each side of the equation, and we get that the volume of the Earth relative to the volume of the shell would be radius of the Earth cubed over 1/2 radius of the Earth cubed. That of course would give us then that the volume of the shell would be 1/8 the volume of the Earth. So proportionally, the mass of the shell would be 1/8 the mass of the Earth. Therefore, using 1/8 the mass of the Earth, we could calculate that the groundhog would weigh only 24 newtons, not the 500 newtons that we initially theorized. So, applying this concept further, what would the groundhog weigh if it could actually get to the center of the Earth? Now, let's see at what point between the Earth and the Moon will a capsule, like the Apollo capsules that went to the Moon, where they will experience a net gravitational pull. So if this is our Earth and there's our Moon, there's our capsule, we understand that this is going to occur at a displacement that is much closer to the Moon than to the Earth. Remember, R does not stand for radius in these problems, but it stands for distance between the object centers. So the sum of our forces would be 0. The force of attraction between the Earth and the capsule and the force of attraction between the Moon and the capsule would be equal and opposite. Substituting in using Newton's universal gravitation and canceling out common variables, we can see that we would get the radius of the Moon, or the displacement, I should say, from the Moon to the capsule relative to the displacement of the Earth to the capsule will be equal to the square root of the mass of the Moon to the mass of the Earth. Substituting in those values that we look up or are provided with, and we get 0.111 as a ratio. So from that, we can solve understanding the distance being about 240,000 miles between the Earth and the Moon, that distance is going to occur between about 210,000 miles from the Earth and about 26,000 or so miles from the Moon. We also want to discuss at this time in our gravitation unit Kepler's laws of planetary motion. And Kepler devised 3 laws of planetary motion that we've come to accept and understand. And the first is that planets orbit in ellipses, not circles, with one focus being the sun and the other focus being an undetermined point in space. That's Kepler's first law. Eccentricity, we should point out at this stage, is a value that refers to how oval-shaped essentially the elliptical orbit is. So in other words, the deviation of the orbit, the ellipse, from being a pure circle. And we will discuss more on eccentricity later. Kepler's second law of planetary motion says that as planets move, they sweep out equal areas in equal times. What this means is that as a planet is closer to the sun, it must be moving faster in order to sweep out the same equal area. So in this graphic we can see that S1 and S2 are equal areas, and obviously the arc length of S1 is more than the arc length of S2, which means that the object, whatever planet this is, the speed as it travels around closer to the sun must be greater than the speed that it travels farther away from the sun. Kepler's third law of planetary motion relates the period to the distance the planet is from the sun, specifically stating that the period squared is directly proportional to the mean distance from the sun cubed at any point along the planet's orbit. So period squared over distance from the sun cubed equals a constant value. Similar results can be derived from this, for example, relating period squared to the semi-major axis, which we'll call A here. The semi-major axis, of course, is the quote-unquote longer axis of the ellipse, and semi-major means we're cutting it in half. So period squared to the semi-major axis cubed would also be a constant value. And we can even derive an equation relating Newton's universal gravitational constant and the mass of the body. Period squared to semi-major axis cubed would be equal to 4 pi squared over Newton's universal gravitational constant and the mass of the orbiting body. These are equations we won't use a whole lot in this course, but we will examine them in this unit with some depth. Again, we now provide some sample problems for you to test your understanding, work on these problems, and bring any questions you may have with these problems or about these problems to class so that we can discuss them.